You know, from the bristles on your toothbrush to the carpet under your feet, polyamide fibers are literally everywhere. We usually know them by their famous trade name, nylon. But have you ever stopped to wonder how these incredible materials are actually made? And what's the real difference between the two most common types, nylon 6 and nylon 666? Well, today we're going to unravel that science.
So, here's our game plan. We'll start with the absolute basics of what makes a polyamide. Then we'll jump right into the specific recipes for both nylon 6 and nylon 66. After that, we'll put them head-to-head to compare their properties, and we'll finish up by taking a look at how chemists are engineering the nylons of the future. Let's get into it.
Okay, first things first. What exactly makes a polyamide? Well, a polyamide. It all comes down to a very specific chemical link.
At its heart, a polyamide is a polymer. And a polymer is just a fancy word for a long, long chain of repeating molecules. What makes it a polyamide is that these molecules are all linked together by something called an amide group. You know, nature actually figured this out first. Protein fibers like silk and wool, those are natural polyamides. But in the textile world, when we talk about polyamides, we're really talking about nylon.
And the story of nylon is pretty cool. It all started back in the 1930s with a brilliant chemist named Wallace Carothers over at DuPont. His work led to the world's first truly synthetic fiber, nylon 66, which hit the market in 1939. But what's absolutely wild is that in the very same year, a guy named Paul Schlack over in Germany discovered a different version, nylon 6, using a totally separate chemical pathway. It was this crazy case of near-simultaneous invention that really set the stage for the two parallel nylon industries we have today.
So that brings us to these two titans, nylon 6 and nylon 66. And those names aren't just random. Nope, they're a direct clue to their chemical makeup. Specifically, they tell you the number of carbon atoms in their fundamental building blocks.
And right here, this slide shows you the fundamental difference. It's so important. Nylon 6 is built from just a single type of building block, or monomer. It's a ring-shaped molecule called caprolactam, and yep, you guessed it, it has 6 carbon atoms. Nylon 66, on the other hand, is made from 2 different monomers, adipic acid and hexamethylene diamine, and each of those has 6 carbon atoms, hence 6,6. This one little difference in the starting ingredients means their manufacturing processes are completely different.
Okay, so let's cook up some nylon 6. The modern way to do this is a continuous process that polymerizes that one single monomer, caprolactam. It really breaks down into 4 main stages. First, you got to prepare the initial mix. Then comes the actual polymerization reaction. After that, there's a super important purification step. And finally, you form the polymer chips that are going to get spun into fiber.
Now, step 1 is critical. You start with molten caprolactam, and you mix in about 10% water. Now, you might think the water is just a solvent, but it's not. Here, the water is actually the catalyst. It's what kicks off the whole reaction by breaking open that caprolactam ring. You also add in some stabilizers to control the final properties of the polymer.
All right, let's get to the heart of the process, the VK tube. I want you to picture this massive, heated, stainless steel tower, about 8 to 10 meters tall. The molten mix gets fed into the very top, and then it slowly zigzags its way down over 12 to 24 hours. The high heat and that long journey give the monomers plenty of time to link up into long polymer chains. But here's the catch. The reaction never fully completes. It kind of runs out of steam and reaches an equilibrium, leaving about 10% of unreacted caprolactam just hanging out in the final mix.
And that brings us to an absolutely critical step. You have to get rid of that leftover 10% of monomer. So the molten polymer is cooled, it's cut into little chips, and then it's washed, like really thoroughly, with hot water. This dissolves and removes all that residual caprolactam. This purification step is essential if you want a high-quality polymer that can be spun into strong, consistent fibers.
Okay, time to switch gears and talk about nylon 66. Because it starts with 2 different monomers, the process is completely different. It's a 2-stage chemical dance. First, you have to create this perfectly balanced intermediate salt from your 2 monomers, and then, in the second stage, you polymerize that salt to get your final product.
The entire success of nylon 666 really hinges on this first step. You take adipic acid, that's the A, and hexamethylene diamine, that's the H, and you react them in methanol. The absolute key here, and I can't stress this enough, is getting the ratio exactly 1:1. If you're even a little bit off, it'll limit how long your polymer chains can grow. The reaction creates what's called AH salt, and it conveniently precipitates out, which locks in that perfect ratio for the next stage. Pretty clever.
So you take that AH salt, dissolve it in water, and then you pump it into this giant pressure cooker called an autoclave. It gets heated up to around 270 degrees Celsius under some serious pressure. This is where the magic happens. It's called polycondensation. The individual salt units link together, releasing water molecules as they go, and form those long, strong polymer chains of nylon 6,6.
Now check this out. The amount of water that's created and then has to be removed is just staggering. A full 13.5% of the starting material's weight is lost as water during this reaction. Now compare that to nylon 6, where you only lose about 2% of the material in the washing stage. This really highlights a huge difference in material efficiency between the two processes.
So, we've got two different recipes, we're starting with different ingredients. How does that all translate to the final product? Does it even matter? Oh yeah, it matters. Let's compare their properties.
Okay, looking at this table, you'll see they are surprisingly similar in a lot of ways, right? Same density, very similar strength or tenacity, and they absorb about the same amount of moisture. But look at the melting temperature. This is the big one. This is the single biggest difference. Nylon 6,6 melts at around 260 degrees Celsius. That's a full 45 degrees higher than nylon 6. This superior heat resistance is exactly why you'll find nylon 6,6 in more demanding applications, like parts under the hood of your car or in high-performance outdoor gear.
Chemically speaking, again, they're very similar, but nylon 6,6 has a slight edge. Its molecular structure is a bit more symmetrical, and that allows for stronger bonds to form between the polymer chains. This gives it slightly better resistance to things like acids and alkalis. For most everyday stuff, though, their performance is pretty much identical.
Of course, chemists are never happy just leaving things as they are. The real magic, the really cool stuff, happens when they start tweaking the base polymer to create modified nylons for very specific jobs.
We're just going to touch on 4 key modifications here that have had a massive impact on the textile industry, especially when it comes to creating smarter, more functional fabrics.
Have you ever gotten a static shock from walking on a carpet? Yeah, me too. Well, anti-static nylons are the solution to that. By adding certain compounds, like polyglycol ethers, right into the polymer mix, manufacturers can actually make the fiber more electrically conductive. This allows any static charge to just dissipate safely, making carpets and clothes way more comfortable and less prone to that annoying static cling.
Okay, this is where polymer chemistry gets seriously clever. By controlling the number of specific chemical groups at the ends of the polymer chains, you can precisely control how the fiber accepts dye. This lets manufacturers weave different types of nylon fibers together into a single fabric and then, in one single dye bath, create these incredibly complex, multicolored patterns. It's the secret behind so many of those intricate carpet and upholstery designs you see everywhere.
You know, from its discovery in a lab back in the 30s, all the way to the engineered fabrics of today, nylon's journey has just been one of constant innovation. It's an incredible story of polymer science, and it leaves us with a really fascinating question to think about. What's next? I mean, just imagine self-healing nylons, or fabrics that change color on command, maybe even textiles that conduct electricity to power our devices. The possibilities, they're truly endless.